So far, we have always considered the case of direct measurements, that is, when the measuring system provides the value of the measurand directly. In this case, we have also discussed the methods for evaluating standard uncertainty. However, there are many important cases in which the quantity of interest is measured indirectly, by mathematically combining the measured values of other quantities. For example, a speed is obtained by dividing the distance traveled by the time taken to cover it. A density is obtained by dividing a mass by volume, electrical power in DC systems by multiplying a voltage by a current, electrical resistance by dividing a voltage by a current, and so on. More generally, a quantity y can be obtained from n other quantities x1, x2 up to xn according to a function f, as you can see here. The quantities capital X are measured by obtaining estimates small x1, small x2 up to small xn, which, when combined according to the same function f, provide an estimate small y of quantity capital Y, as you can see here. Now, x1, x2, xn are measurement results. Each of them is therefore associated with the standard uncertainty u of x1, u of x2 to u of xn, evaluated using one of the methods we have seen in other videos. The problem we need to solve is how to obtain from these values a standard uncertainty u of y to associate with the measured value y, in order to turn it into a measurement result. To do this, we need to make a few assumptions. The first is that the function f is linear. This is not always the case, but we can assume that the function is linear in the neighborhood of y, and this is plausible since we are assuming a measurement uncertainty that is small compared to the measured value, and therefore small variations in the values of x. Under these assumptions, function f can be expanded in a Taylor series expansion about the mathematical expectations or expected values μ of the input variables x, and the expansions can be stopped at the first term. The deviation of the measured value y from its expected value μ y is therefore given by the relation you see here, in which the expected values of the input variables x and of variable y are always linked by function f. However, let's pay attention to this point. The partial derivatives you see in this equation should be evaluated at the expected values of the variables x. These values, however, are not known, so the derivatives are instead evaluated at the measured values, introducing a small unavoidable approximation. If all derivatives were zero, or if a function f were strongly nonlinear, even in the neighborhood of y, it would be necessary to consider higher order terms in the Taylor series expansion. Fortunately, in the vast majority of practical applications, this is not necessary. Let's continue with the mathematical formulation of the problem and square both sides of the equation obtained. As you can see, on the right-hand side, we have the square of a polynomial. If we expand it, we obtain this equation. We can now consider the expected values for the squares of the deviations between the measured value and the expected value. As you can see here, the expected value of the square of the deviation between y and μy is the variance sigma y squared of the probability density function of the random variable capital Y, which represents the measurement result. Therefore, it is the square of the desired standard uncertainty associated with small y. Similarly, the expected value of the square of the deviation between x and their respective μ is, as you can see here, the variance sigma I squared of the probability function of the random variable capital Xi, which represents the result of the direct measurements. Therefore, it is the square of the standard uncertainty associated with xi. The matter is a little more complex for the expected values of the cross products xi minus mi I and xj minus mi j. In probability theory, this expected value is the covariance between the random variables capital Xi and capital Xj, as you can see here. It expresses the probabilistic dependence between the two variables. Zero covariance means that the two variables vary in a completely independent manner. As the covariance increases, the two variables become dependent, in the sense that if one takes on values greater or smaller than its mean, the other also takes on greater or smaller values. Covariance can also be negative, in which case if one variable takes on larger values, the other takes on smaller values. By substituting the expected values into the equation we saw earlier, we obtain the equation you see here, which gives us the standard uncertainty associated with the calculated value small y for quantity capital Y. This equation can be rewritten by normalizing the covariance between xi and xj to the product of the standard uncertainties u of xi and u of xj, as you can see in this equation. In this way, we obtain the correlation coefficient R, which, due to the properties of the covariance, is symmetric and ranges between -1 and +1. You can then obtain the equation you see here, which is known as the uncertainty propagation law and which provides the standard uncertainty, called the combined standard uncertainty, associated with the result of an indirect measurement. As you can see, the combined standard uncertainty is given by the square root of the sum of two terms. The first is a weighted sum of variances and therefore always positive terms, where the variances are given by the squares of the standard uncertainties associated with the measured values of quantities xi, and the weights are given by the squares of the partial derivatives of function f with respect to variables xi. These derivatives are sensitivity coefficients that indicate how sensitive the output value of function f is to variations in the input values. If the value of the partial derivative relating to quantity xi is small, a relatively large uncertainty in its measurement can be tolerated. Conversely, if the partial derivative is large, it should be measured with a small uncertainty in order not to have a large uncertainty on the value of y. The second term is a weighted sum of covariances and takes into account the dependence or correlation of a measured value xi on another measured value xj. The weights are always given by the partial derivatives and can result in either a positive or negative contribution depending on their sign. The presence of correlation can therefore contribute either to increasing or decreasing, depending on the sign, the combined standard uncertainty. In the case of no correlation, the second term is zero and the uncertainty propagation law is simplified as you can see here. To summarize, we have seen how to obtain, in the case of indirect measurements, the combined standard uncertainty to be associated with the result of the indirect measurement, starting from the standard uncertainties associated with the directly measured individual values. We have also seen that any dependence between the measured values can increase or decrease the uncertainty on the final value compared to the case of completely independent measurements. Finally, we have seen that the standard uncertainties and the covariances are weighted by sensitivity coefficients, which take into account the sensitivity of function f and therefore of the measurand to variations in the input quantities and thus to the variability of the directly measured values.